In this video, we're going to look at sections 15.5 through 15.7 of your textbook, 15.5 through 15.7. Now, we're going to put them all together because some of the sections are very short, but also they're so interrelated that it's difficult to separate some of these topics from others. So we're going to consider angular momentum, relation between moment of a force and angular momentum, and the principle of angular impulsive momentum. We're going to look at those sections. Again, they're sections 15.5 through 15.7 in your textbook. And so angular momentum can be thought of as the moment of linear momentum about some point O. And so let's just look at a couple basic examples. Again, almost goes back to the idea of moment that you had from statics and solid mechanics. So you have like some object here. You have like maybe some moment arm, say 2 meters. Then you have this moving at a velocity of 10 meters per second. And let's say it's 3 kilograms. And so if you want to find the angular momentum about O, and so it's something like this. And let's say we have, so you can sort of think of it this way. It's going to be, say, the angular momentum is usually represented by H. So again, usually angular momentum may be H. Let me put this up here somewhere, like H would be like the angular momentum. So H about point O is going to be, again, think of like you had from solid mechanics, a force. So if you had a moment, it's going to be a force times a distance. So in this case, we're going to have our linear momentum, mv, times the distance r. So it's very similar. You have your moment arm r, and then your linear momentum is m times v. So in our case, we have our mass was 3 kilograms. And then our velocity was 10 meters per second. And then our moment arm was 2 meters. And this is going to be like 60 kilogram meters squared per second. And so the same thing if you were in solid mechanics and your velocity was not, say, perpendicular to the motion, or you didn't know exactly what the motion was, you can break it down into components. So like, for example, let's see if you have an example like this. Maybe you have something out here. This is like 5 feet. and maybe 5 feet here, and maybe this like 8 feet up here. And so your ball or your object's right here. Here like this. Let me focus out a little bit. And so this is 8 here. And then let's say that the velocity is 9 feet per second. So we have 9 feet per second, but it's at an angle of, say, 15 degrees. And once again, we have the point O, the origin, and we have 12-pound ball. And so once again, you could actually sort of find the moment arm if you wanted to, or just like in solid mechanics, you break it up into components. So if we want to find the magnitude of angular momentum, about O. So we could do it, like I said, in components. So let's say if we did that, so we have this ball out here. If this is 15 degrees, and this is 9, you can see that our y component is going to be 9 cosine 15 degrees, which is going to be like around 8.7 feet per second. Our x component is going to be 9 sine 15 degrees, which is going to be about 2.33 feet per second. And then this is at 5. And we said this one is at 8. So again, you could do this with components. So your 8 about the point. Once again, if you do counterclockwise positive, usually what we did in solid mechanics, it's going to be, like I showed before, your m times v, excuse me, sorry. Your m times v, and that's going to be 12 divided by 32.2. And times your velocity. Let's say first we'll do and say the x direction. So 2.33. And then let's see, if we do in the x direction, our moment arm, you see, is going to be 8. So again, this is our mass, our velocity. This is our moment arm, r. Again, this first part was in the x direction. And then plus, same thing, 12 divided by 32.2, the mass, times the velocity in the y direction, 8.7. mv. And then our moment arm in the y direction would be 5. That's be our r, like this. So again, this is x. This is for x. This is for y. Then you put that in your calculator again, 23.1 or 2. Let me do 23.2 pounds feet second. Any questions on that? Just some pretty basic things. And then just like we did in solid mechanics, there's a vector version as well. You remember we had like a vector version if you had like something in 3 dimensions. We're probably not going to use it too much, but let me write it down. Angular momentum in vector form. And so if you had, say, something in 3 dimensions, and you had some object out here, had some mass to it, and then again you had some moment arm R, and it was moving with some velocity in vector form. Then your HO in vector form is going to be R cross MV. Again, where R is the distance in terms of a vector, V is the velocity of your object in vector form. So it's R cross MV. And then so this would be the vector form of what we just had of the MVR, and this of course is the scalar from the one we just did. So this is the vector form, we just did the scalar form. So that's angular momentum, and what we want to do is put this together with angular impulse. So before we had impulse and momentum, linear impulse and momentum. Now we're going to have angular impulse and momentum. So this is 15-7. And so just like before, remember we had impulse and momentum. So now we're going to have similar thing, HO, say 1 plus the summation T1, T2, MODT is equal to HOT. And this is the initial angular momentum. And this is angular impulse. This is final angular momentum. And so again, this MO, this could be MO maybe given to you. In the form of a moment. So that would be like, say, pound-foot or Newton meters. Or you may be given a force and like a moment arm. as with most of the problems in dynamics, it's the best way to learn these is just to go through problems, and we'll see how this is applied. Next, we're going to take a look at this problem, F15-24. F15-24 says two identical 10-kilogram spheres are attached to the light rigid rod, which rotates in the horizontal plane centered at pin 0. Now, the fact that it says light, I guess we're to assume that we can neglect the weight of the rods, because it says the rods are light, so let's assume we can neglect the weight of those. And the balls rotate on the horizontal plane center at pin O. If the spheres are subject to tangential forces of 10 newtons, and the rod is subjected to a couple moment of 8t Newton meters, where t is in seconds, determine the speed of the spheres at the instant t is 4 seconds. The system starts from rest. Neglect the size of the spheres. So again, we have these spheres rotating. Notice they're in the horizontal plane, so it's a two-dimensional problem. And now notice we have a moment applied, 8t. Now there's a force of 10 newtons, but that's at a distance of 0.5 meters from the center. So that's also going to result in a moment. And this is 0.5 meters. 0.5 meters here. And we have a force of 10 newtons here. Force of 10 newtons here. And so we're going to have a force applied over here and over here. And also there's going to be a moment about O. And it's going to be 8t like this. And this is in Newton meters. So it's 8t Newton meters. So it's going to be this moment about the center here. So this starts from rest. And find the speed after 4 seconds. So we'll take a look at that. So we've got these two spheres here. They're going around the center, each at 0.5 meters from the center. Each have two forces on it. And then we also have this moment here. Again, these forces are constant, but you can see the moment is variable based on time. So let's put all this together. So solution. So keep in mind that we want to use like HO1 plus the summation T1, T2, MODT equals HO2. So we keep that in mind. And so remember the momentum that we're going to have. So let's write this down. So our angular momentum is always going to be like mv1 times our moment arm plus, now for the moment here, we have two things. We have this 8t. And so let me just put the moment down. We're going to integrate that. So from say T1 to T2. Plus we have the moment caused by these 10 newtons. So that's going to be some force times distance, delta t. And right hand side, we have mv2 and our moment arm is not going to change, so just keep that as R. So we can now put in some numbers here. This is going to be, again, starting from rest. So let's just make that 0 right away here. So it's going to be 0. And then for moment, it's going to be 8t times dt. And we're going from 0 to 4 seconds. And then over for our forces, we have two 10-Newton forces. And the moment arm on those is 0.5 dt. Now, actually, you'll notice here we didn't really need to integrate this because this force is going to be constant. I'll put it under the integral anyway. It goes from 0 to 4. And the right-hand side, we have two 10-kilogram masses. And we don't know what the final velocity is. And the moment arm is 0.5, like this. So if we integrate this thing here, we get 8t squared divided by 2 from 0 to 4 plus this is going to be 10t 0 to 4. Like I said, this one here, we could have just written this as 2 times 10 times 0.5 times 4. I wouldn't need to integrate it, but I did it just to show. And on the right-hand side, we have 10 V2. And if we put our bounds in, put the 4 in here, and put the 4 in here, and the lower bound 0. So it's going to be 8, 4 squared divided by 2 plus 10 times 4, 10 V2. And put this in your calculator, around 10.4 meters per second. Next, we're going to look at this problem, 15-103. 15-103. The 4-pound ball is traveling in a circle. Now, at the beginning, the circle is R1 is 3 feet. The radius is 3 feet at the beginning. And is moving with a speed of 6 feet per second. That's tangentially 6 feet per second. But there's a cord, and the ball is being pulled towards the center of this disc. As you can see in the picture, the cord is being pulled at 2 feet per second. And they want us to determine the ball's speed at the instant that radius is 2 feet. So at the beginning, the radius is 3 feet, and this cord is pulling through the center, going to pull the ball towards the center of the disc. And they want to know the speed when the ball has a radius of 2 foot. Also, how much work has to be done to pull down the cord. Neglect friction and the size of the ball. This is 3 feet. It's moving at 6 feet per second. And it's being pulled down through the table. In other words, being pulled in the radial direction at the 2 feet per second. And it's a 4-pound ball. So it's starting out with a radius of 3 feet. And what is the ball speed once it gets pulled to 2 feet? and how much work is done pulling the ball. So we'll take a look at this. And so once again, keep in mind your equation. And I notice this time there's no force, like, no force in the tangential direction, and also no moment applied. So this is 0 because in effect there's no moment. And again, so let's write our equations down here. So we're going to have mv1 times r plus 0 is mv2 times r. Now remember, r is changing, so we probably should have put an r1 here and an r2 over here. And then we're going to have our mass is going to be 4 pounds divided by 32.2 times 6 foot per second times 3 foot. And then the mass is going to stay the same, 0.2 times our V2. And we want to know what's going to happen when the radius is 2. And notice actually, since this is 0, all these masses will cancel, won't they? So this can actually cancel out right there, huh? So we just have 18 on one side and 2 on the other. So looks like V2 is going to be 9 feet per second. And remember, this is the tangential velocity. And so the total velocity, remember the radial velocity is constant. So your total velocity, VT2, is going to be the square root of VR2 plus VT2, tangential 2. So I'm calling this V the tangential velocity. So this would be the square root of 2 squared plus 9 squared. And if you put that in your calculator, like 9.22 feet per second. So that's the total velocity. So I should say total. Let me call that just total velocity, so it's clear. Total velocity. Once the ball is at a radius of 3 feet. Most important thing we had to find was this tangential velocity. So it also wants to know how much work is done. And I realized when they, based on the answer they had in the back, they're assuming that at time 0, the ball hasn't been started to be pulled in yet. So therefore, like the radial velocity at time 0 is going to be 0. So to find work done, use work energy. And so it's going to be T1, B1 to 2 is T2, 1/2 mv1 squared, 1 to 2, 1/2 mv2 squared. And so it's 1/2 4 times 32.2. And the like I said, the original velocity is just at 6 feet per second. So we're assuming at the beginning there's no radial velocity. Then the final velocity is 9.22 squared. And then just throw everything in your calculator. So the work done is going to be, we put all this in your calculator, it's around 3.04 foot-pounds. That's the total work done. Next, we're going to look at this problem, 15-100. 15-100. We have two balls rotating around this rod, and each of the balls is 10 kilograms, and it's subject to a torque or moment of t squared plus 2 Newton meters, where t is in seconds. Determine the speed of each ball when t is 3 seconds. Each ball has a speed of 2 meters per second when t is 0. In other words, you're starting with a velocity of 2 meters per second, subject to this torque, and they're spinning about this rod. Again, this is similar to the first problem we did, but it's good to have as many examples as we can to get used to doing these. Now, also notice this looks like a 3-dimensional problem, but the balls are staying like in one plane. They're not like going up and down. So we can actually treat this as a 2-dimensional problem. Just real quickly, just apply our equations. So summation. And now again, it's shown in 3 dimensions, but everything is really happening just in 2 dimensions. And it's about that point, that small point. So I don't know if you want to call this, you can call this MO or MZ just to stay in the Z direction. Better. DT is going to be H. Let's say that should be H, maybe HO1, HO2. And so it should be like MV1. R is going to be constant in this case, plus the integral of mdt equals mv2r. Then put everything in. Once again, you're going to have 2 masses. So it's going to be 2 times 10 kilograms. And your velocity is 2 meters per second. Your radius is 0.5 meters. And you're going from 0 to 3 seconds, and you're given at the moment. And on the right-hand side, you have 2 times 10 also. V2, your radius is still 0.5. And if you put all this is 20. Integrate this as t cubed over 3 plus 2t. From 0 to 3, right-hand side, that's 10 times V2. And if you put all this stuff in your, substitute the 3 as 27 divided by 3 plus 2 times 3. The lower bound is 0, so we didn't have to include it, so it's 10 V2. And if you put all this in your calculator, I got V2 was 3.5 meters per second. That's actually pretty similar to the first one we did.